and thank you for the invitation. It's my privilege and honor to be a special place and talk about our research. So my name is Yoon Kyoung Cho, and my name is Yoon Kyoung Cho, and I'm from South Korea. Here is my disclosure. Yesterday I was attending a pitch competition, and here myself, the technology that I'm going to talk about today are commercialized by two companies. One is Clinomics, and the other one is Lab Spinner. Before I talk about the applications where we actually deliver the impact for the patient, maybe I'll just introduce the technology behind. In the morning, I heard from one of the gentlemen there, by the time when you don't care about the technology behind, it's actually maybe the good point. But since I'm an engineer and I'm trying to introduce what kind of technology I use, so here is a lab on a disk. Maybe I hope some of you heard about microfluidics and lab on a chip. As the word stands for, actually we want to build a lab on a disk. And previously, we talked about many lab on a chips, and actually myself as one of the associate editor of the journal Lab on a Chip. But even though we deliver the many great science using small devices like chips, but we didn't really deliver the lab on a chip so they can be used in point-of-care diagnostic applications. So when I was working in Samsung already more than 10 years ago, we decided to build a lab on a disk. So by having disk, what we can do is we can actually spin them like a centrifuge, not in a tube, but in a disk format. And we can do so many applications, including biomedical applications, which I'm going to talk about today. But also we can do lots of protein analysis, molecular analysis, and even analyze the water for the toxins or food, whether the food contains pathogens, or use it for the energy applications as well. So how it works is as simple as you spin and there's a centrifugal force push the liquid. But we actually want to have a control on the disk so that my first students and myself, we also developed a valve that you can actually deliver the certain amount of liquid at one time to the different sections. It can be fully automated by using small devices like this. And the application that I'm going to talk about is actually personalized medicine. I heard many of you here is the healthcare providers. As a patient, if you have a disease, when you go meet the doctor and doctor give you a prescription, we actually hope that the drug will work for me. These statistics actually gave a huge motivation for myself. These numbers, like for here, cancer drugs, if you see 75% of the patient would not get the benefit of those prescribed drugs. That's actually very bad, in my opinion. So how can we actually improve that? The concept people talked about, not only me, but many community here is talking about is the personalized medicine. Instead of giving the same drug for many different people, maybe we can actually check the patient and categorize them and give the right drug at the right timing for the right people. So that's we call personalized medicine. Here I am as an engineer. We want to provide the right tool so that the process can be more efficient. Compared to the tissue biopsy, which is very invasive and difficult to achieve, maybe liquid biopsy using biological samples like blood or urine or anything, it may be more quick and less invasive, and also we can give a more frequent monitoring of the disease itself. So here I'm going to introduce a few examples of circulating biomarkers, like circulating tumor cells or exosomes or circulating tumor DNA, how we can isolate them and give the right information for the physicians as well as the patient. So first example is a Ctc Isolation Device. Maybe some of you heard about the Ctc, circulating tumor cells. The tumors are circulating in our bloodstreams, they find a second home, and metastasis happens. So what if we can actually detect these traces of the tumor from the blood, and then maybe we can learn about the current disease status. However, the problem is cells are cancer cells are so rare. So we actually want you to develop a system that works even in small hospitals. So here we load the blood and small centrifuge and spin them. We can actually, the blood is filtered through this little filter, and the bigger cells, like cancer cells, are trapped on top of the filter, and other RBCs and small cells go to the waste channel, and you can wash them, you can stain them, you can identify how many cancer cells are there. One can also use that information to count, and the recovery yield is like good, and it's highly reproducible. And therefore, we brought this system and implemented it in Brigham and Women's Hospital in Boston. And we compared to the only one FDA-approved cell search system cannot count less epichem, low epichem cells, but we can provide a good result. And from the patient sample, we got much better result. And therefore, we can actually detect the metastasis as well as we can detect the mutations, not only from the tissues, but also these circulating tumor biomarkers. And finally, we can actually use it for monitoring of the patient, and we can highly correlate those number of circulating tumor cells. If they increase, it actually gives a poor outcome for the patient. If it is the other way around, it actually reflects the better consequences. Cancer cells are heterogeneous, so we actually take out the individual cells and understand the heterogeneity of the individual cells as well. This device is now commercialized and implemented both in Korea, in US, and Europe. And hopefully maybe if you guys are in India want to take advantage of it, maybe we can talk about it later. Much easier example is the circulating tumor DNA. Cancer cells secrete the DNA, and they are circulating in the blood, and maybe they can be used for the better diagnostics, prognostics, as well as the treatment monitoring. However, these are tiny amounts, so small, and therefore, if we can isolate them as soon as possible when the blood is withdrawn, that could be the better. So we made a device, and let me show you the movie, how it works. So the blood sample, it's sedimented. Plasma is automatically prepared. And then this plasma goes to the next chamber, mixed with the lysis buffer, they bound. And this bead chamber, in a fully automated manner, using small tabletop centrifuge, now you can have purified and enriched cancer-associated DNAs. Using that information as a proof of concept, we try to use the mutation development for the lung cancer patient. So in Asia, EGFR is the biggest mutation. The first drug, of course, works in the beginning, but as time goes by, the patient develops second mutations and the drug doesn't work anymore. By the time, it's better to change the type of drug. But the problem is, patients and physicians do not know when those mutations develop. So here is one example of the patient. We counted the number of CTCs, and we also detected the mutations of the patient as the time goes by. As you can see, this patient, the first drug actually works in the beginning, but as time goes by, it doesn't work. And both CT images as well as the blood analysis, we can tell the mutation increases. And by the time the doctor changed the drug, now the patient go back to the right track. So even though we did this monitoring, by the time when the patient visits the hospital to take a CT images, but what if the patient give the blood in a more frequent time, maybe we can detect these mutations much earlier. So this is called liquid biopsy and targeted therapy and personalized medicine. The last example I'm going to talk about is extrasolar vesicles that we isolate from the urine sample. And EVs are known to be a good molecule, nano-sized vesicles. They contain DNAs and proteins and RNAs and so on, and they participate for the cell-to-cell communication. Oh, okay. We isolate the EVs, and we can visualize them. And as one example, we tested for the prostate cancer patient. So if the prostate cancer patient have a mutation called ARV7, the drug would not give a benefit for the patient. So we selected the patient with prostate cancer and check whether the patient has a mutations or not by using the urine samples. And so from the patient, we can identify the mutations using extrasolar vesicles inside of the urine sample and can give a better benefits. Again, this device has been commercialized and can be used in the hospital settings for the research purpose at the moment. I'm going to share the last one and then maybe close. This is work with my good students, Isaac Michael. And this experiment is very special because we made a small portable device. Without electricity, we can isolate the bacteria from the patient urine. Currently, without checking whether the patient has a bacteria or not, the physicians provide antibiotics. That's what I was told here. However, by using the devices, like a small, low-cost, electricity-free, we can isolate the bacteria and even see the origin of the type of bacteria. Maybe we can prescribe the right antibiotics for only those for those people who need antibiotics. So the system, how it works is like this. It's a small centrifuge device, like a fidget, like a toy for the children, and urine sample can go in this small toy. Resolutions are not really good, but and then you can spin them, and we can enrich the bacteria on top of these small devices, and then we can just add a color reagent, and we can see whether the patient has a bacteria or not. And if we treat the antibiotics with and without antibiotics, we can actually tell the type of antibiotics works for this specific patient or not. So to make a long story short, we actually brought these devices, and here, Tendai Hospital, Kaveri Hospital, and we tested the Indian patient here, and it actually works better than cell culture, but in a much, much shorter time. And we further developed that. We treated with antibiotics, and we can tell whether the patient, the right antibiotics working that for specific patient. So to conclude, I appreciate my group members, and especially the student Isaac Michael, who made the whole my first travel to India possible. And thank you for your attention.